on. Next up is Nins, he'll be talking about the software engineering part of data science. Nins is a software engineer in the Philippines. He has worked with several startups in the past and currently works at Hakoras, focusing on back-end and machine learning integration. He is currently taking his master's degree in computer science in the Philippines. His interests are astronomy, physics, and cooking. This is a pre-record talk, so Nins will be on Venulus answering questions. Take it away.
Hi, good morning. So, I'm Nins and welcome to my presentation here at PyCon Australia 2020. I'm gonna be talking about the software engineering side of data science. So hopefully there's gonna be a lot of learning for you guys because all of these are based on my experience working on a data science team as, a software engineer. So let's get started. I'm a machine learning engineer at Hakarus for about a little shy of 4 years. I'm studying masters in computer science here in the Philippines at Ateneo de Manila University. I love playing music, I love astronomy and physics, and as you might know, I love to tinker around with a lot of data stuff, and I'm always curious. So if you have any other questions, you can hit me anytime or send me a tweet or a DM. Yeah, so let's begin. First, I want to discuss about what's the difference between data science and software engineering. Let's try to understand first where all of this stuff is coming from, and we'll try to see if there are any kind of similarities between the two fields. The next one is we're gonna discuss the challenges that software engineers are facing while working in the data science team. I'm sure there are quite a lot of people who have experienced the same thing because data science and software engineering are getting more and more intertwined recently. And I think this is the beef of my talk. So the third point that I want to discuss are the problems that we encounter. What kind of challenges are we experiencing daily? And what are the solutions to these problems? We're gonna talk about very specific problems such as deployment, collaboration with each team, and code review and code quality control. And lastly, if you're a software engineer, what's it going to be for you if you want to shift into a more data science related role? So we're gonna give some bit of advice and tips so that you can proceed with your data science career coming from a software engineering standpoint. Okay, so first things first, let's try to differentiate the difference between software engineers and data scientists. I know there can be a lot of interpretations from different people, so I asked a couple of my friends to give some of their very brief understanding of what the differences between the two industries are. So here we go, let's just watch them.
Hi, I'm Stephen and I'm a data science student. So while I don't really have a solid background in software engineering, I would say that the biggest difference between data science and software engineering is that while both fields try to look for solutions, the foundations of software engineering is more on the computer science aspect, whereas data science, the foundation is more on the math and statistics aspect. So with data science, you will have things as simple as exploratory data analysis or visualization, or you can go to something more complex like chatbots or some heavy machine learning engineering.
So data science deals more on presenting and analyzing data, while software engineering deals on creating software. In data science, you'll focus more on the data you have or you will gather. Based on those data, you can do computations, data comparisons, and analysis to come up with sound result. It can also be used to predict trends. Software engineering, on the other hand, focuses more on creating applications that can be used by users. You will work on creating features, user interfaces, and user experience to make an app that the target user can use.
Hi there, PyCon audience. Let me briefly give you my idea of the difference between data science and software engineering. In software engineering, the biggest uncertainty we need to deal with is users' behavior. That is, it is quite hard for you to expect exactly how your software will be used by users in advance. Therefore, being flexible while keeping your software quality is important to absorb this uncertainty. Data science, on the other hand, needs to face uncertainty and statistical nature of data itself. Since pursuing accuracy in the process of building models can be an endless journey, data scientists like to use programming to facilitate rapid trials and errors. So simply put, the speed of trials and errors is crucial to handle the uncertainty in data science.
Thank you very much for those very insightful answers, and I'm pretty sure we all have our own understanding of what software engineering is versus what a data science is. So software engineers tend to focus more on the code quality, while data scientists focus on the model accuracy. Software engineers also put a priority on the maintainability of the software, while data scientists are more concerned about getting insights from the data. Software engineers tend to tinker about different architectures and create several boilerplates for the projects, while data scientists focus their time on how they can visualize their data. Software engineers are also more user-oriented compared to the data-driven approach of data science. And while software engineering focuses more on the actual software output, data science is more on mathematical computations and statistics. These are the key differences between the two fields. Of course, there are so many other differences between the two, but I think when you ask most people, this is what they're gonna tell you. But for now, let's focus on software engineers. Because I myself came from a software engineering background, and I've worked with several data science teams in the past, and I'm also working with the data science team right now. And there are several challenges that software engineers face when working in a data science team. The first one, and I think this relates to me the most, is the code from the data scientists sometimes are not efficient, and I think it's not written up to standards, which is totally okay, because we have to remember that they are data scientists and not software engineers. So the second one is that models are often based on limited training and testing data. This is actually a big problem because when you take the models and apply it into a certain application, the models or the result of the model sometimes are different from the result of the initial prototype. And also sometimes the models are not designed to take in large amount of data sets. This causes problem in production. The next one is data formats. So I always find myself talking to data scientists about what are the inputs and what are the outputs of the algorithm. And more often than not, we are encountering problems about data format because we don't have a proper standard for the input and output. So this is definitely a big challenge for us. And then the last one is how do we actually deploy the models? I have had several experiences where I need to deploy the model on edge devices, which have very little amount of resource. Sometimes we deploy it in the cloud, which we can scale up anytime. You need to be able to understand what kind of production environment the application will use. And then for the very last item, please provide documentation. Please always document your work for the data scientists and for the software engineers, because it's very hard to understand each other while just reading the code. It's always important to have documentation. The goal with working with data scientists is always simple. The first one is we need to provide a reliable AI product for our customers. And then the next one is to be able to provide proper insight with a given set of data. And I think if the software engineers and data scientists can work hand in hand and improve their collaboration, then we can definitely achieve this goal. Fortunately, Python bridges the gap between data scientists and software engineers. Aside from the fact that it's a common language between the two industries, I think Python is easy to understand. You can set it up consistently using several tools, and it's ideal for fast prototyping for both data scientists and software engineers. So let's dive into the specific development challenges that software engineers encounter while working in the data science field. I want to focus on 3 specific pointers here, which is mainly the collaboration setup, how the data scientists and software engineers work together. I want to focus also on performance considerations. So this is for the deployment of the algorithms and for the integration of the machine learning code to the software engineer or to the application code. Lastly, we'll try to discuss several production setup for your finished application. We'll look at how we can deploy applications in a small scale setup versus deploying the application in a large scale setup. The first one is collaboration setup. If your initial setup for collaboration is not good or there are no protocols in place, then everything will kind of fall off. Let's start with how do we actually organize a proper project template and bootstrap for our data science projects. As a software engineer, it is our duty to create a base project template for the data scientist to use. This ensures that several standards or several project structures is always in place even though we're working on different kinds of projects. One thing that I find useful is that when I give credentials to the data scientists for them to use in different kinds of integrations such as Amazon, Google, we try to manage the credentials properly. It's very important that you assign one credential per one data scientist so that you know who's actually using their credentials and using the services. Most of you are familiar with Git hooks, I assume, hopefully. In our setup, we utilize Git hooks a lot. For example, we use pre-commit and pre-push for our test hooks as well as our linters and the other boring stuff that we can automate, such as basic code checking. Lastly, for the initial project setup, you need to be able to provide test templates for both notebooks and packages to data scientists. This is very useful because testing is actually a software engineering job and it's more oriented towards creating a code base that is testable. At the same time, you can actually know the proper coverage of the tests. So the second one is about environment management. I'm sure you're all familiar that it's very difficult to share your work with others if you have different kinds of environment. Some of us uses Mac, some of us uses Windows. So it's important to have a standard environment that everyone can use. How do we manage our environment when we're working with data scientists? One of the things that I find very useful is we use Docker for notebooks and other package tools. In this way, we're quite sure that the same library that I use in my setup will be the same library that one data scientist can use in his or her setup. The second one is, I'm not sure if you're familiar, but I really suggest you look into this, is Poetry. Poetry is some sort of like a replacement for pipenv, but it includes packaging and distribution tools as well. So for development purposes, I highly recommend using Poetry to our data scientists because it's very flexible and you can edit the requirements right away. Unlike Docker, that it's kind of defined already, Poetry is very ideal for the actual development environment for each data scientist or software engineer. One thing that I also emphasize is we need to separate development dependencies to the actual production dependencies. This is very important because when you start packaging these algorithms and models, some of them can be really bloated, and any kind of library that we can take off from the package will definitely save some sort of memory or storage. The next one is about code quality, and I think we should really focus on this because it's our job as software engineers to make sure that the quality of code or software that is delivered is at the highest. In this specific section, I am going to try to show you several code examples, and I hope that by showing you these code examples, you can apply them into your own machine learning project or any kind of machine learning tools. The first one that I want to emphasize is since data scientists don't actually have or don't actually use PyCharm or some very powerful editor, so we try to integrate tools like Flake8 and PyLint so that the code for the data scientist has proper formatting and all those manual stuff can be automated easily. The next one is we try to use type hints every time. If you're not familiar with type hints, I'm gonna show an example later. And then we try to standardize our error handling. This is very important in a sense that if you have a good error handling and if you have proper error messages, it is easy to communicate to data scientists about the problems in their code. We also use data classes. We utilize this because it's easier for the data scientists to use rather than for them to create their own kinds of classes. I'm gonna show an example later. We also use interface. This is personally one of my favorite because it's sort of like an object-oriented concept, but at the same time, it's very useful for machine learning development and integration because it ensures that several code structures are always the same throughout the entire project. Let's dive deeply into the code now. We have a class user, and as you can see here, we assign a specific type to each variable. So some editors actually utilize type hints to ensure that there are proper input and output for each function that is being called. It's also very useful because aside from checking the proper data type, developers can look at the function and see what kind of data type is being used for each variable. So this acts some sort of documentation as well. The next one is an example of how we try to handle errors. We don't just rely on simple print messages or simple return true or false. We actually create classes that describes what kind of error actually happened. As you can see in this example, if let's say for example the model is not fitted, then we specifically create a class for not fitted exception and for other similar types of errors. This next example right here is about defining custom classes and creating data classes. This code is an example of what we did before, where instead of just passing an array or a list of data, we actually created a class for training data. Here you can see that there are three properties, which are mainly data, label, and we included some sort of metadata in case you want to add additional information on the data that you're passing to the model. One of the reasons why we use data classes is that first, if you compare the code from the previous one, it's quite straightforward and it's quite simple to understand. You can also easily include type hints when declaring data classes. So this one is about interface classes, which has an abstract method, fit, and predict. So this is to ensure that the data scientist will implement the fit and predict function. Lastly, for the collaboration setup, I want to talk about CI and CD. So software engineers are the ones responsible for doing this. We need to be able to set up automation pipelines in GitHub, GitLab, or whatever tool are you using, preventing unauthorized commits and all those stuff. One thing that we recently followed is automatic docs generation. This is very useful for multiple projects because we are quite sure that we have the proper documentation each time there is a merge request to the master branch. It's very difficult to keep track of the package versions. We also integrated this into our pipelines, and every time that a pull request is merged to the master branch, it will automatically create a version and package of that specific library and upload it to our PyPy repository. The next section, I want to talk about the performance considerations that software engineers need to keep in mind while working on a data science team. I think this is a very good representation of our expectations versus the reality of how the models or the algorithms work sometimes. The first point that I want to emphasize is we need to understand the CPU and memory limitations of the algorithm or of the model. I think it's important for us to understand several machine learning algorithms and how they actually work. It is also quite important to benchmark the models using incremental data inputs. Later in the slide, I will show some sort of comparison between two models. We also need to understand the difference between threads and processes. In my experience, traditional machine learning approach performs well in threads, while deep learning approach and neural networks performs well when using multiprocessing. The next thing that I want to discuss is about model storage and distribution. So for high traffic applications, don't ever store the model in memory. High traffic applications sometimes are erratic and sometimes behaves unexpectedly. So if there's a sudden surge of data and your model retrains itself, it will just consume a lot of memory and your application might crash or might die. It's always safe to architect your application in such a way that it can safely load a pickle file once it trains or retrains a model. We need to make sure that the code structure is pickle safe. This means that when you pickle a model and when you load it into a different application or a different environment, the pickle file should still work. Lastly, I want to discuss about interface options. So if you want to integrate the models created by the data scientists to an application, then you'll need to decide on what kind of tools you will use. In my experience, we try to integrate models to web applications. Sometimes we use batch jobs or task queues. You need to identify the frequency of model use. You need to understand how many times the model will be trained, how many times the model will predict data, how many times does the model will be retrained or be reused, or even how many times does the model will be loaded from a pickle file. Lighter frameworks are ideal because they consume less resource and they are not as bloated as other tools. Lastly, you need to avoid combining process or threads because it might cause memory leaks or other resource management problems. Now let's focus our attention in this graph. In this graph, we're trying to compare two models using their CPU utilization, memory consumption, and model size. The first model seems to have a problem with CPU utilization when it reaches 1000 input, while the second model is having difficulty in memory consumption as well as model size. This could mean that we're trying to store lots of unnecessary information as the data grows bigger for the second model. While in the first model, it can also mean that we probably need to increase the CPU resource of the machine because it seems to have an exponential growth. So the final point that I want to discuss is about production setup. Depending on whether you want to deploy your application on a Raspberry Pi or you want to build a full-fledged AUS setup, you need to consider the following considerations so that your application can run smoothly and efficiently. The first thing you need to identify is the target environment of your application. Do you want to run it in cloud or do you want to run it in edge devices? There are pros and cons for different types of deployment. Cloud has an infinite resource while edge devices has very limited resource. Edge devices are cheap while cloud environment is a bit expensive. Also, if you're gearing towards training, inference, and high load application, maybe you need to deploy it in the cloud. While if you're looking for data gathering and inference type of AI applications, then you can go with edge devices. Once you have a target environment, you need to know and understand time and space complexity of the algorithms and models. You have to remember that an O of n squared in the local setup or in development setup will still be an O of n squared in the production setup or even in a cloud infrastructure. My suggestion is to target an O of n log n for both time and space complexity. This is kind of the sweet spot. Lastly, you have to consider the platform and the hardware dependencies of the libraries that the machine learning application uses. One example is OpenCV. OpenCV actually doesn't have any ARM-based builds that you can use right away, so you need to build it yourself. Another example is Torch and PyTorch, which has no GPU support for Mac. Now that we have discussed some of the day-to-day challenges and solutions, the one thing that I want you to remember is that data scientists are not software engineers. We just need to work hand in hand with the data scientist and give them feedback in case something's wrong with the actual model or the actual algorithm. The final part of my presentation deals with how to become a data scientist if you're a software engineer. Now, my first suggestion is to just get a formal degree and study data science in your university. Data science requires lots of mathematics and statistics, and it's very difficult to learn this online or on your own. The next tip is if you can find related jobs to data science, it's also a good start. You can first start with an internship or you can start with applying as a data engineer. I came from a software engineering background and I gradually worked myself into my current position, which is a machine learning engineer at Hackarus. And finally, I just want to tell everyone that data science and machine learning will become more accessible in the future as tools and platform. The best way to secure your career is to study the foundation of data science to be able to give meaningful insights and drive business decision. This is where the true value of data science comes in. And that's the end of my presentation. So I hope you learned something new from me, and I hope that you have lots of takeaways from this talk. If you want to work as a data scientist, then I wish you luck, and I hope to see you someday in the data science field. Thank you again for attending my presentation, and big thanks to PyCon Australia for giving me this opportunity to share this information with you. Have a good day, everyone.